All right, so we talked about centripetal acceleration. We talked about what it means to travel in a circle at a uniform speed. Okay, now we're going to look at the force that causes that to happen. Okay, centripetal force can work in both uniform and non-uniform circular motion. But we're going to look at it just initially just from a uniform circular motion perspective where the speed is not changing. Okay, so circular motion cannot occur without this force pulling into the center. We already talked about why. In order to move in a circle, there has to be an acceleration towards the center. To have an acceleration, there has to be a force, a net force that is causing it. So essentially, really, centripetal force is the net force acting on an object moving in a circle. Okay, it's not a separate force. It's the sum of all the forces acting on that object. As long as the net force is towards the center, the object will accelerate towards the center. Okay, so centripetal force really is the net force for an object moving in a circle. Okay. Understand that many forces can act as centripetal forces. We've already identified tension, friction, and gravity. Okay, there's others. Learn how centripetal forces operate. Basically, they pull things toward the middle of circles, strangely enough, okay? Being that they are center-seeking forces. Right? And then understand how banked curves use Newton's third law to produce greater centripetal force. A banked curve is what we typically use at an interchange. Okay, an exit ramp, an off ramp, or an on ramp, okay, that has those curves on it, right? Okay, you turn away and it's always banked like the one just out here to get back onto the QE2, okay? So we got that bank corner with the speed limit on 60, something like that. I don't know. I take it at 60 most of the time. Whatever, okay? It's banked, okay? The reason it's banked is, well, banking a corner helps in two ways. Banking a corner means the corner can be smaller, okay? And secondly, it can guarantee a safe speed regardless of the road conditions. Okay, based on the angle of bank, you can make it so that a car could traverse that corner at a specified speed and not slide out or in to the corner for that matter. Okay, I've actually seen a car that in really icy conditions didn't slide out of an exit ramp corner, actually slid into the middle of it because they were going not too fast, too slow. Okay, if you are overcautious, that can be just as dangerous in really icy conditions. Okay, and I could see it happening because I was coming in. This person was already halfway through the corner, and I could see them just like crawling. There's that one. Well, it's gone now. It used to be at the McLeod and well, now it's 22X interchange there. It used to come on that way. And this car, I could see it was going just really, really slow, and I could see them starting to come down the face of the corner. I'm like, that guy is going to go into the middle because he's not going fast enough. So I came into the corner, okay, and I was going exactly the speed limit, which is what you need to do in that situation. Any faster, you slide out. Any slower, you slide in. It was practically frictionless. It was so slippery. And this guy actually slid right in. There was nothing he could do because it was so slippery, he couldn't speed up. Okay, when he tried to speed up, the tires just spun and he slid right into the middle of the corner. Okay, everybody else slid into the guardrails. Okay, he slid into the middle. Well, I went all the way around because physics is awesome. And if you understand physics, things work out well for you. Okay, all right. So Newton's second law tells us that we can calculate net force by going mass times acceleration. Well, we learned in the last lesson, okay, that centripetal acceleration is v squared over r. So if I want to calculate the net force in a circle, I take mass and I multiply it by the centripetal acceleration. And there is Newton's second law applied to a circle. The net force in a circle, the centripetal force, is mass times speed squared over radius. All right, that will be your most fundamental formula for this unit. It's on your formula sheet, but we will use that one as much as we used m times a in the last unit. That is m times a for this unit. All right. Now, if we're looking at this formula, let's just see if we can figure out some of the relationships here. Right? If I increase the mass, what will happen to the centripetal force? It'll increase linearly, exponentially, inversely. Okay, think about last unit. If I increased mass, what happened to force? It increased In what way? Linearly. Well, it's still the same here. Okay, mass isn't, there's no exponent on mass. We're not dividing by mass, we're multiplying by it. So if I double the mass, I'll double the centripetal force. Okay, and we already looked at the relationship between radius and centripetal acceleration, so we know it's going to have the same relationship with centripetal force. An increase in radius will result in a linearly smaller centripetal force. Okay, that's an inverse relationship. What about for speed? It's exponential. So that means if I take that corner out there at the speed limit, I'll have no problem. If I take it at twice the speed limit, I need 4 times as much force to hold me in the corner. Okay, I am relying on friction being able to magically provide me with 4 times the force it was providing at the speed limit in order to keep me in the corner. Okay, so if the speed limit is 60, my chances of traversing that corner at 120 are pretty slim. Don't try it. Okay, your chances of traversing that corner at 120 are slim to none. All right, unless you were in like a very, very high-end sports car that was very low slung. Okay, now what do we often see happens to cars if they don't slide out of a corner? They often what? They take it too fast. They could spin out, or if they're like a tall truck, they can tip. Yeah, they can flip over or tip. Okay, this was a big problem with some of the early SUVs. Okay, that came out in kind of the 90s and stuff. They had all these dangers of rollover all the time because their center of mass was very high. Same is true for a semi truck or a moving van or anything like that. If you pack a lot of mass near the top, there's a lot of inertia at the top, and that inertia wants to leave the circle. Okay, more so than the bottom of the vehicle, and that can cause the vehicle to tip. Okay, to tip over. All right, so you have to be mindful of that if you're driving a vehicle that is tall. Okay, there's more of a danger of tipping it or rolling it because of that. All right. All right, so we just have to remember, guys, that this is essentially calculating F net. Okay, the centripetal force is the net force for an object moving in a circle. It's the vector sum of all the forces acting on that object in or out of the circle. It's easier than what we did in the last unit because there won't be any angled forces. Okay, they'll either be out of the circle or into the circle, and that's it. Okay. All right, so like you said, some cases it's easy to identify the centripetal force because you can see it. If there's a rope attached to something, you know that's the tension in the rope. Okay, but if it's something orbiting something else, well, that might be a little tougher. Okay, that might be gravity. Okay, you know, if it's an object going around a corner, a car going around a corner, we don't necessarily see the friction, but it's there. Okay, it gets trickier when we're talking about electric forces and magnetic forces. All right. Back when we used to use like cathode ray tube televisions, the ones with the big glass tube, okay, those actually used magnetic and electric fields to divert and change the path of particles that would smash into the front of the tube. Okay, you'd have these particles that hit the front of the tube, and that would create the light patterns on the tube. Okay, but there was a big giant magnet at the back of these TV sets. Okay, and they would just alter the path of the particles. Okay, and cause them to hit different parts of the screen and produce the picture. Right? It was actually quite an ingenious thing, but now it's way easier to do that with projection, okay, and LCD and stuff like that. Okay, but again, that would be a magnetic force that's altering or curving the path of a particle that would otherwise want to go straight towards the center. Okay, we apply the magnetic force and we cause it to change direction instead. All right, so effective speed on centripetal force. We were saying, just looking at the formula, that this should be an exponential relationship. All right, so if I have this model airplane that's being whirled in a circle that has a mass of 0.9 kilograms and it's moving at a constant speed, we want to find the tension in the string, that would be the centripetal force, for speeds of 19 and 38 meters per second if it's on a 17-meter line. All right, so what the question has given us is the radius. 17 meters, that's how long the line is. Okay, it's given us the mass of the plane, 0.9 kilograms, and it's given us the 2 different speeds that we want to compare. So to calculate centripetal force, I'm going to take mass times speed squared over r, so that'll be 0.9 times 19 squared divided by 17 meters. All right, so in the first situation, my centripetal force will be 19.1 newtons. Okay, what will it be in the second situation where I'm going 38 meters per second? 4 times that. Okay, should be 4 times. It should be looking at like 72 or something like that. Okay, so we'll just double check it here. 0.9 times 38 squared. Okay, divided by 17. All right, 76. All right, if I divide that by 4, okay, I get 19.111. Okay, so it's an exponential relationship clearly, okay, between speed and centripetal force. Okay, so the faster something moves, we would require exponentially more force to keep it in a corner. Okay. All right, effective radius on centripetal force. We've already said that likely the relationship here is that as radius increases, centripetal force will decrease. So if we're looking at that, okay, we would just plug in those numbers again. So now we're going to keep the speed at 28 meters per second, and we're going to use the same plane, but now we're going to use 11 meters and 22 meters. What we find is for the smaller radius, the centripetal force is 64 newtons. Okay, for the larger radius, half that. So we doubled the radius, we got half as much force. So inverse relationship, okay, in increasing the radius will linearly decrease the centripetal force in that situation. All right, so if I would take a corner a little bit wider, I'm less likely to spin out. If you ever watched any like NASCAR or anything like that, okay, the guys that usually lose it on the corner are the guys who are going on the inside, right? They're trying to pass somebody on the inside. Okay, if they do that, they're trying to go faster in a spot where they need more centripetal force to hold them in the corner. Okay, which is why when they go, they take everybody else out. Okay, because everyone else is wider up on the corner, they lose it and they slide up the corner and into everyone else. If you pass someone on the outside, you have to go a lot faster than you do on the inside, but you have much greater chance of not losing your cornering ability passing on the outside. Okay, but you have to be able to go faster. Okay, what do you do in racing in order to help you do that, to make that pass? The slingshot, yeah, shake and bake. Okay, yeah. All right, so you got to do what's essentially called drafting. That is, you tuck in behind another car, and by tucking in behind that car, you reduce the amount of air resistance acting on your vehicle because the air is passing up and over the car in front of you, which allows your engine to not work as hard to maintain that speed. Then you can pull out quickly, okay, get a bit of acceleration before you slam into that wall of air, okay, that allows you to pass the car in front of you that's working harder. Right? So in racing, it's a delicate balance. When you're trying to go by somebody, okay, or you're leading the race, it's tougher to lead than it is to be the guy that's trying to pass, okay, because your car is having to work harder being in the lead position. Okay. All right, so when a car moves at a steady speed around an unbanked corner, so that's a corner that's level, the force that acts as a centripetal force is friction, static friction in this case. Okay? Static friction is what keeps you in an unbanked corner. What if I drift it? I'm cooler, definitely. Okay, but am I relying on static or kinetic friction if I drift the corner? Kinetic. Now, also the key with drifting is that I can't take the corner like this by steering my car around the corner. I have to change the angle at which my car is traveling because I need the back wheels to do what? I need them not only to slide, but I need them to spin and provide a force that is at least directed somewhat towards the center of the circle. Okay, so if you're drifting, you go from being at this angle, come on, okay, you alter the angle of the car so that as the wheels spin, okay, and you kind of turn it like this, okay, the wheels are then providing a force towards the center of the circle, directed towards the center. They're pushing that way, okay, and that's what can try and keep you in that corner. But of course, when you get towards the apex of the corner, you need to do what? You need to straighten, okay? If you don't, you're just going to chop a donut. Okay, that's incidentally how you do that. Okay, if you're chopping a donut, you just keep that angle and you go around in a circle and you make a cool tire skid shaped circle that looks like a donut. Okay, on the road. Okay, if you don't want to do that, okay, you just want to get around the corner, then at the apex of the corner, you have to essentially let off the gas a little bit in order to allow the tires to regain their traction before you mash on the pedal again and propel forwards. All right, because if you continue to spin, you'll lose that traction. Okay, you won't gain it back, and you won't be able to change direction again. Okay. All right, I want you guys to try this one here. Compare the maximum speeds at which a car can safely, oh, sorry, we got to go over this. I haven't shown you how to do this yet. Okay, so we want to look at the maximum speeds a car can negotiate an unbanked curve in dry weather, where there's lots of friction, and icy weather, where there's 1/9 the friction. Okay, we got a coefficient of friction in dry weather of 0.9, coefficient of friction in icy weather, okay, of 0.1. So we already said that when you go around an unbanked corner, it's friction that is providing the centripetal force. Okay, so that means then that the force of friction is equal to the centripetal force. That essentially becomes the challenge of this unit. What force or forces are adding up to Fc? Most of the time it's just one force. Okay, it's this force equals the centripetal force. In this case, the force of friction is the centripetal force. All right, formula for force of friction is mu times the normal force, which on a level surface is equal to force of gravity. So instead of writing Fn, I'm just going to write mg. Everyone okay with that? Okay. Formula for centripetal force is mv squared over r. The question wants us to calculate how fast the car can take the corner in various conditions. Okay. Did it ever tell us the mass of the car? Is that going to be a problem? No, because it's going to cancel. Look, mass is on both sides. Okay, it actually doesn't matter the mass of the car here because the coefficient of friction is the same and gravity affects them both equally, okay, in terms of the acceleration. All right, so I'm going to manipulate and try and find v here. So I first have to move r, so I'm going to multiply both sides by r, cancel my m's, and I'm going to have this. Mu times g times r equals v squared. I don't want v to be squared, so I'm going to square root it. So to find v, I'm going to take the square root of mu-ger. You'd be surprised how often that ends up being the formula. Square root of mu-ger. Okay. All right. So we've got this formula now set up. Now I just need to plug in my numbers. Under dry conditions, where mu was 0.9 times 9.81 times the radius of the corner, which they said was 50 meters. The car can traverse the corner at 21 meters per second. Okay. In the icy conditions, I have 1/9 as much friction. So my speed will be how much of this number? Not 1/9. I'm square rooting it. No other way. 1/3. Because the square root of 1/9 is 1/3. Okay, so it's still an exponential relationship. Okay, but we're looking now at this situation. So we'll have 0.1 times 9.81 times 50. Okay, that should come out to around 7 meters per second, but we'll double check it. Okay, 7.00. Tanner. Because it's the one that's keeping the car in the corner, right? It's the force that keeps it turning. Yeah. Okay. If this was like, someone going around a corner by holding onto a rope attached to the light post at the corner, then it would be tension. Yeah. All right. We'll leave it at that. Okay. And we'll talk some more about centripetal force tomorrow. Okay. There won't be a quiz tomorrow because we haven't gone over enough stuff yet. Okay, so you're getting a break on quizzes here over the next little while. Okay, but we will be moving straight into that tomorrow.